Okay, so this video is going to review some key items from Chapter 16, Deflection of Beams, and then Chapter 18, Combined Loading. Okay, so first off, we're going to talk about Chapter 16, Deflection of Beams. Now, there's three types of problems. If you take a look at the practice problems that I gave you guys, you'll see that there's three types of problems. The first one is going to be talking about curvature. The second one's going to be talking about finding deflection of beams with formula method. And the last one is going to be about superposition. Now, superposition is basically when we have a couple different methods and we can calculate them separately and add them together at the end. So we'll be going through that individually here. Okay, so the first type of problem is with curvature. So if we take a look at this, the equation that we need to use is sigma equals EC over rho. Now the equation that we'll need to use EC over rho, C is basically the radius of the wire diameter that's being bent, and rho is the radius of curvature. So for the first practice problem here, we have a steel rod that has an 1/8 inch in diameter. It's bent into a loop of 10 feet, and we need to figure out what the stress is. So if we go ahead and go through the problem, we are going to use this equation here, you'll see, that I just mentioned. And we basically just plug in the numbers into the equation and get what we need. E is the modulus of elasticity for steel. We have 30 times 10 to the 6. And for the radius, the diameter was an 1/8 inch. So we take half of that. And then this here, this 5 times 12, is simply the 10 feet divided in half. But then we have to convert it to inches because it was originally given in feet. And we end up getting this stress here. So that's one type of problem. Now, if you look at problem number 4, it's another type of problem here. And we need to figure out the minimum diameter of the coil that the wire can be wound if the flexural stress, the allowable stress, is 60 megapascals. It's the same equation that we used before in problem number 1, but in this case, what we're going to do is we're kind of working backwards. We're given the stress, and we need to find the radius of curvature for it. Okay, so here we go. There's the equation. In this case, we're solving for rho. And you can see I reformat the equation here, and this is what I get. This is the allowable, this is the modulus of elasticity. This is the radius of the wire, and this is the allowable stress. And it gives us the, if we go through the calculation, it's pretty straightforward. You can see I get a radius of curvature of 2 meters that I'm allowed to have. Okay, so the next type of problem is going to be calculating deflections with formulas. So here what we have is we have a wide flange beam. It's used in a 30-foot simple span. We have to compute the maximum deflection due to a concentrated load at the midspan. Okay, so it's a simply supported beam, and we have a load of 12 kips going down. Okay, so if we take a look at here, we take a look at the solution. We need to look at table 16-1, and that's on page 581 in our books. If you take a look at that, there are 8 cases. We need to find the case that's going to work best for a situation. And in our case, for this particular problem, we're going to use case 5. And we're going to solve for the maximum deflection at the load. So you can see that this equation here is the equation that I got directly from page 581. So I put this in, and I have to look at the picture to determine what the items are that I need. Okay, so P is the load here. Okay, L is the length. Okay, I've got the 48, which is a constant. I've got my E, which is the modulus of elasticity, and my I value I can get directly from the back of the book in the tables. And I do the calculation, and then I go ahead and I get my 0.868. Now the last type of problem is superposition. This is for problem 15. If you take a look at this, you'll see that there's a picture that's drawn. I've got a cantilever beam. It's got a load that's kind of at the center, And then I also have a distributed load. There's no one direct case that will satisfy every condition here. So what I have to do is I have to use the formula method, but basically split it up into two pieces. That way I can solve it separately and then add the solution together. If I take a look at this, my two conditions are concentrated and distributed. I use the table 16-1 on page 581, and I find the concentrated load and the distributed load deflection formulas, and they're listed right here. Here's the concentrated formula, and here is the distributed formula. So what I'm going to do next is I'm going to go ahead and I'm going to calculate those separately. So for the concentrated, you'll see that what I've done is I've gone ahead and separated everything out for you. There's the equation, and I put the values in. I'll let you take a look at those. And then for the distributed load, we've got the items put into the formula there. Then, after we get these two deflections, all we need to do is basically add them together to get our overall deflections. These problems are very nice because we can calculate those deflections separately and then add them together at the end. Okay, so now we're going to move on to Chapter 18, Combined Stresses. Now you'll see that there are several problems that I have listed on the practice. You don't have to do all of them. We're going to worry about three of the problems. We're going to worry about number 1, which is combined loading. We're going to look at number 29, which is stresses on an inclined plane. And we're also going to look at Moore's circle. Okay, combined loading. The other two problems, the 8-9 and 8-17, 18-9 and 18-17. If you'd like to look at them, you can, but we're going to skip those for the online section of this course. If I go ahead and go to the PowerPoint, and I'm located here, we're going to look at problem number 1, and this is for the combined loading. And also, I'm going to go back to the key concepts and equation sheet that you should have available to you. So if you take a look at the key concepts and equation sheet, when you look at axial and bending stress, you're going to calculate these separately and then add them algebraically. So if you take a look at this, you see these formulas that I'm highlighting right here. We're basically stretching the beam at the same time that we're bending it. So what we're going to do, it's a lot like superposition, where we're going to calculate the normal stress from the pulling of the beam, and then we're going to calculate the bending stress from the bending portion, and then we're going to add them together. Now, one thing you'll see here is that we've got to be very careful. One of these is negative, and then one of these is positive in some cases. So basically, it's adding those numbers together, and you'll see that when we get into the PowerPoint. So with this here, we have a wide flange beam of 16 by 50 section. It's got a simple span of 20 feet. It's subjected to a uniform load of 2 kips per foot and an axial tensile force of 10 kips. So I'm trying to pull it from its section with 10 kips of force, and I'm also bending it. So we need to figure out what the maximum tensile and compressive stresses are in the beam. Okay? Now, from the appendix, I got to look up some information, and I get this directly from the appendix, from the wide flange 16 by 50 area. For the simple span, the maximum bending moment is calculated, and this here is from table 13.1. Okay, and remember we looked at that in chapter 13. Because this bending moment is positive, the top of the beam is going to be in compression, and the bottom of the beam is in tension. Okay, that's very important to know, because what that will do is that will allow us to figure out what our signs are when we add all the stresses together. Okay, then what we're going to do is we're going to calculate the stress on the bottom. Okay, and then we'll calculate the stress on the top. You'll notice that the normal stress is positive here because we're trying to pull it apart. It's in tension. And then what we're doing here for the bottom, okay, there we go, that's positive here, and then this one is negative here, okay? So the normal stress is very simply calculated with the values that we looked up from the appendix. okay, the 10,000 and the 14.7. And then we're going to go ahead and put the M and the S, the M that we calculated, and the S, which is also taken directly from the appendix. And we do those calculations and we add our numbers up, and this is what we get. Okay, so the top part is intention, and we can see that 15,495 psi is the issue. And then we also have 14,134 in compression for the bottom. Okay, so for the next problem, number 29, this figure is very important. You'll see that in the book, when you do your calculation problem, you're going to see something that looks like this. If this arrow is supposed to be for sigma y is pointing up, it is positive. It is pointing down, it's negative. For sigma x, if it's pointing to the left, pointing to the right, my fault, it is positive. If it's pointing to the left, it's negative. And for tau x, if it's pointing straight up, it should be positive. If it's pointing down, it should be negative. So we're going to look at the calculation problem that we have, and this is the figure that we have. We have to figure out what the stresses are, and you can see that this 50 megapascals is negative, and this 50 megapascals here is going to be positive. So all we really need to do is just to use that figure there, just to make sure that we have the correct sign. And then we're going to go ahead and write those values in. Our tau is 0, it wasn't present, and our angle is 45 degrees. So we use these formulas that were given here, and we just substitute our numbers in, and we calculate what our final values are. It's very straightforward. We can go ahead and substitute those numbers in, and then we get our final answers here. So it's pretty straightforward. It should be pretty good. Okay. The last type of problem that we're going to look at is something called Moore's circle. Now, Moore's circle, you can see we use the same type of diagram here. And Moore's circle is basically a graphical way of calculating some stresses. So we're going to have our values here. And the key things to note with Moore's circle is that we need to do a couple way calculations first. First, we need to write down all our given information and make sure that we put the signs and they're located here. Two things that we need to calculate are the center of the circle here and then point V, which is going to be used to help us draw our graph. Now, if you guys were drawing these, I would highly recommend using a CAD system to be able to do that. Okay. First, we're going to set up our axis system, okay, like so. And then we plot our point C, we plot our point V. Then we go ahead and draw our circle and draw our radius. Now, continuing on with Moore's circle, what we're going to do is we're going to use that angle 30 degrees that we were given and draw from point V, because that's the point we need to start with, up to something called point P. Then we're going to carry down, okay, cross down from point P all the way down to the other side of the circle. We're kind of making like an upside down V here, and that's point S. And point S is basically where we want to actually take our other values from. Okay, so this would be the answer to the problem. Now for your homework, you're going to be calculating the C and the V. And I'm not asking you to calculate point S. I'm just asking you how you would actually draw the, how you would draw the Moore circle for yourself. Okay? So if you need to review that again, you can pause and rewind and watch it again. Good luck.